there are three models that we're going to be working with that describe the different properties of light. One of them is a wave model that describes the wave properties. One of them is the photon model, which describes the particle-like properties. And one of them is the ray model that describes how light bends through different materials. We're going to define a light ray as a line in the direction in which radiation energy flows. So for example, here's a light bulb. I have light coming out of it. The different arrows coming out represent the light rays, which are the direction that light energy is flowing. Now, we're going to consider different sources of light rays. One source is just going to be a point source. So you can imagine this to be an infinitely tiny little speck of dot that's giving off light. So for example, if I'm looking at a star from very, very far away, that's going to be a point source. It's going to be giving off light radially in all directions. We also have a parallel ray source. So if I have a flat screen TV that's just giving off white light, it's giving off light pretty much straightforward. We're going to call that a parallel ray source. Now, it's important to note that these definitions of sources depend a little bit on how exactly I'm looking at the object. So for example, a very, very far away star may look like a point source, but if I'm on the surface of the star, that surface is going to look pretty flat in the same way that the Earth looks flat if you look at it up close. So it could look like a parallel ray source. Similarly, if I'm looking at my TV from a very, very far distance, the TV is going to look like a little dot, so it may look like a point source. So these are just, these characterizations of point source and parallel ray source are really just approximations for what we have in the real world. One of the things that light does is reflect. So we're going to talk about reflection. So I have here a mirror, just a nice little mirror, and also a white sheet of paper. Now, both of these are reflecting light. What's the difference between the two of them? White material reflects light, mirrors reflect light, but why can I see my reflection in the mirror, whereas I cannot see my reflection in the sheet of paper? Well, let's take a look. Here's a mirror. Here's me. I can see myself in that mirror. I get a mirror image of myself in the mirror. However, like paper, I see nothing. I just see white. So mirror gives me reflection. Paper, not so much. What's going on there? Well, if I zoom in to the mirror on a molecular scale, on a microscopic scale, what I see, say this is my mirror, what you see is that it's very, very smooth. In contrast, paper is very, very rough on a tiny scale. So if I were to look at the light rays that are coming into the mirror, what you would see is that a sizable percentage of them come in like this. Here's a few, they're all coming in. And they are going to reflect back, but they're all going to reflect back in unison. So that any image created by the light that came in is going to be reflected back almost exactly. If I try the same thing with light rays going into a rough surface, like a piece of paper, they're not going to be reflected back in unison. This one might get reflected back this way, this one might get reflected back this way, this one might get reflected back that way, because the surface is rough. Having a rough surface means the angle that the light is going to get reflected is going to be very, very randomized. So that is why when I look at a piece of paper, I see just a white mess of light, whereas if I look at a mirror, I see an actual reflection of what's going on. Let's see if we can describe that mathematically. I've got a light ray coming in, a light ray coming back out. I will call this the incident light ray because it's incident on the surface. I will call this the reflected light ray because it's the light ray that reflects back. We want to come up with a law that describes these two quantities. Now I should warn you, this is going to be the most complicated equation you will ever see in your physics life. It is that the angle of incidence is equal to the angle of reflection. That's it. Just angle of incidence equals angle of reflection. Mirrors are pretty straightforward because I know whatever angle you come in at, that's the angle that the light ray gets reflected at. The one thing that is a little bit tricky is we need to remember how exactly the angles are measured. The angle is measured relative to this perpendicular line to the surface. So it is not this angle here. It's not the angle relative to something that's parallel to the surface. It's the angle relative to a line that's perpendicular to the surface. All right, let's test your understanding. Here I have a mirror and I have a ball. Here's my eye and I'm looking at the mirror. Where am I going to see the ball? Where am I going to see the mirror image of the ball? Am I going to see it at position 1, position 2, position 3, 4, or 5? I'll give you a few seconds to make your choice, and we'll see what you said. All right, well, let's see. We know the angle of incidence has to equal the angle of reflection. So I can pretty much rule out this one or this one. Because there's no way those are going to be where I see the light. I need something to hit my eye, comes from the ball and bounces off the mirror. So what you can do, let me try to be somewhat neat here. Here we go. I have an incident light ray coming from the ball, coming off and hitting my eye. I have drawn it so that my angle of incidence, angle that the light comes in at, equals my angle of reflection. Now you might be tempted to think that I see this ball, number 4, because that's where the light is hitting the mirror. But I'm not seeing the light hitting the mirror. What I'm seeing is the light coming off of the mirror. What I mean by that is it looks like the light is coming from over here. So the correct answer in this case is answer number 5. It looks like the light is coming from ball 5, not from ball 4. So I'm going to interpret that as the light, as a ball being behind the mirror over here. That's what it looks like. It looks like I'm looking through a piece of glass at a ball that's located right here. So I have here a mirror, and it is a concave mirror. By concave, I mean it's kind of bowl-shaped, and we're looking at the part of it, if this were a spoon, we're looking at the part of it that the soup would go in. So there's a hole in here. And you can see that the image we get from a concave mirror appears to be inverted. Now, why does it appear to be inverted? Well, it's inverted, but if I get really close to the mirror, let's take my finger there, you'll see my finger is not flipped upside down. My head is flipped upside down. My finger is not flipped upside down. Why is my head flipped upside down, but my finger is not flipped upside down? Now let's see what's going to happen when I shine 2 lasers on a converging mirror. This is a mirror that is concave, so it's kind of bowl-shaped. I have my mirror here. I've got my 2 lasers over here. I'm just going to turn these guys on. And let's see what's going to happen. Let me turn my smoke machine on over here so we can visualize that a bit better. And turn off my lights. So there we go. You can see those crossed laser beams reflecting off of my converging mirror. So we're going to be tracing light rays going to the mirror and seeing how they reflect back. Now, there's an important geometric point that we're going to be concerned with called the focal point. And we can find that by tracing 3 lines coming in horizontally and seeing where they intersect. So, first thing I'm going to do is I'm going to shine one line of light. This is one of the few times neatness is actually going to matter, so I'll do this with a meter stick. I'm going to shine one line of laser light straight at the center of the mirror, and that will just reflect back along the path that it came in on. I'll do another line. I'll make this one with a red marker. There we go. I'm going to have another line. So this will be another ray of light. Comes in this way. Now, it's going to reflect back at a different angle because my mirror is curved, so it's going to reflect it down somewhat. So I want to try to make my angle of incidence equal my angle of reflection. So my red light comes in this way, bounces down that way. I will make one more line of laser light. This up. Should take the cap off my marker first. There we go. So the blue light is going to come in like this. I want to look here. I want to make my angle of incidence equal my angle of reflection. And what you will find is that for a curved mirror, all of those lines will intersect at one point. The light will be focused at this particular point, so we call that the focal point. Let's see what type of image a concave mirror makes. We're going to make this with an object that is outside the focal point. So it's not inside the focal point, it's further away from the mirror than the focal point is. We're just going to trace some rays here. First ray I'm going to trace, let's have that ray come in horizontally. So the ray comes in horizontally. And is going to be reflected back through the focal point. It's just a matter of the angle of incidence equaling the angle of reflection. I know rays that come in horizontally get reflected back through the focal point. I can do a similar thing hitting the center of the mirror. Assuming I can line it up. And this light ray comes in, hits the center of the mirror, and it will bounce back at a certain angle. Again, the angle of incidence should equal the angle of reflection. I might want to make this a little bit less sloped. Clean that up a little bit. Here again, you're just using the fact that the angle of incidence is the angle of the reflection. So these two angles are the same. Take that off just so I don't make my diagram too messy. If I keep tracing my red line down, we'll get an intersection around this point right here. Just to check that that is where my image is actually going to be made. Let's see if we can do one more line. Do one more line. So I've hit the center of the mirror. I've came in horizontally and gone out through the focal point. Now let's come in through the focal point. In through the focal point and come out horizontally. We'll come out this way. And you'll see light goes in this way, bounces back this way. You see, we will get an image of the object right here. Well, we can list a few things about it. First of all, we might notice that it is inverted. So when I was looking at the mirror from far away, that's why my head appeared upside down. Because when I look at a concave mirror, at an object that's beyond the focal point, it is going to appear upside down. The other thing we will note about it is that it is a real image, in that if I were to hold up a screen, there is really light hitting it. If the light is really traveling there, so I really do have these red, green, and blue light rays hitting that point, we call that a real image. What happens if I have a concave mirror where my object is in front of the focal point? Well, again, let's just use ray tracing to figure out what's going to happen. So my first ray, let's send that in. It's going to appear to be coming from the focal point. And then it's going to bounce back horizontally. Comes in like this, bounces back horizontally. The next ray I am going to be working with let's have that come into the center of my mirror, and then we'll just use the fact that the angle of incidence is the same as the angle of reflection to figure out where that second light ray goes. Finally, I want to have one light ray that comes in horizontally. So I had one that went in through the focal point and out horizontally. We're going to do one more that comes in horizontally and passes back through the focal point. Okay, where does the light, the reflected light, appear to be coming from? Well, let's see. My red light appears to be coming from somewhere over here. Let's actually trace that out a little bit carefully. My reflected ray appears to be coming from somewhere behind the mirror. My blue light also appears to be coming from behind the mirror. If I can line this up, my reflected ray. My green line appears to be coming from a point behind the lens as well. And if I look where all these points are coming from, and I trace this out, barely have enough room here, but you can see they all appear to be coming from a point over here, from an object that's over here. So my actual object is fairly small, but my image is magnified. So we'll call this our image. We'll see that our image is magnified. What else can we say about our image? Well, it's upright. Both my image and my object are pointing in the same direction. If I get really close to the mirror, let's take my finger there, you'll see my finger is not flipped upside down. However, the light isn't really on this side of the mirror. So I can't actually hold up a screen and project that image onto the screen. I can't use it like a movie projector. So we would say that this would really just be a virtual image. It's not a real image that I can hold a screen up to and then get the image of a picture. It's only going to be a virtual image. Here we have a convex mirror. You can see an image of me, and I look pretty tiny in that image. You can see my thumb looks much, much bigger than my head. Hello, squishing my head. Why do I look so reduced in that mirror if it is convex? So what happens if I put my diverging mirror in there? You can see that those laser beams start going off to different sides. That looks very, very nice. A convex mirror is going to have its focal point at a different spot in space. So let's take a look, trace the light rays now. So my convex mirror here is bulging outward. So it's going to reflect light at a wider angle than it came in at. We're going to start again by drawing a line of light in the middle here. So I'm going to have a green line come in like this. So I shine a light beam in, and since it's right at the center of the mirror, it's just going to reflect back along the line that it came in at. I'll do my next line in red. As before, I'm going to have my red line come in a little bit higher, still coming in horizontally. So my light comes in horizontally. And I hit the mirror at this point. And as always, the angle of incidence is going to equal the angle of reflection. So if I draw the normal there, then I can make my angle of incidence equal the angle of reflection. I can do the same thing with my with one more ray of light. I'm going to try to line this up as much as possible. So that's about 20 centimeters above. I'll get this 20 centimeters below. Just about there. Here we go. Got my blue light coming in. Comes in this way. And as always, we're going to have our angle of incidence equal our angle of reflection. So let's try to draw that. Coming out like this. I can line it up. There we go. Now, how do we find our focal point here? It seems that the green line, red line, and blue line are now spreading out. So it doesn't seem like they intersect at all. Well, that is the case. They don't intersect at all. However, if I were to imagine that the reflected ray is continued beyond the mirror, I'm just imagining this, it's not actually there. But if I look on this side of the mirror, I could imagine that my green line extends. Since this is just us imagining, I'm going to just draw this as a dotted line. You can imagine that the green line extends a bit further. Similarly, the red line would extend a bit further as well. And if you've drawn this correctly, if you've drawn it to scale, which I almost certainly have not, you will find that your red, your green, and your blue all intersect at the same point. So for a convex lens, what you find is that your focal point, this point right here, where the red, green, and blue would all intersect, if they continue that far, we call that the focal point. Well, here is my object. We're going to do some ray tracing. Let's just trace a few rays. First one, let's have that ray go in horizontally. So my incident ray comes in horizontally. We'll have the ray that passes out appear like it's coming through this focal point. So my reflected ray, we can just trace that back down. And it will appear to be passing through that focal point. Up next, we are going to send another ray in. This ray will pass to the center of the mirror. And then we'll just use the fact that the angle of incidence is the angle of reflection to trace the outgoing ray. About here. There's my reflected ray. Finally, let's just recap. We've got a horizontal ray coming in, and then a ray that gets reflected passing through the focal point. We've got a ray that comes to the center and then bounces back from the center. Finally, we're going to have a ray that comes in aimed at the focal point and then bounces back horizontally. Let's try that. Line this up with my focal point and my object. Trace my ray coming in. It will bounce back horizontally. And it's supposed to be straight. So I've drawn my three rays. Let's see where the reflected rays come into focus. Well, we know the red ray appears to be coming from the focal point. The blue reflected ray appears to intersect the red ray at this point. And if I trace my green reflected ray back, it too will appear to be coming from the same point. So what does that mean? It means that we get an image at that point. Now, what are the properties of that image? Well, it's smaller than it was before, so we'd say it's reduced in size. You can see an image of me, and I look pretty tiny in that image. which presumably it has to be, because when I looked at a convex mirror before, I appeared to be much smaller. So if I'm looking at my reflection, I'm going to look a lot smaller. The image that I see of myself is going to be smaller. It's also upright. So I was not flipped upside down. My head was not upside down in the mirror. Finally, we know that the light rays aren't really behind the mirror. They get reflected before they get behind the mirror. So I can't just hold up the screen and make that image. Since I can't make a real image of the object, we call that a virtual image.